Today's problem is submitted by a viewer, and it says, let alpha and beta be the roots of x squared minus x minus 1 equals 0, with alpha greater than beta. For all positive integers n, define a sub n is equal to alpha to the n minus beta to the n over alpha minus beta. And also define b1 is equal to 1, and bn is equal to an minus 1 plus an plus 1. Okay. Then which of the following options is or are correct? The sum of a1 to an is equal to an plus 2 minus 1. Or the sum as n goes for, well, there's a lot of options here. I won't read them all out, but I'll write them so you can see them in the video. Okay, I'm not sure exactly what my first approach is going to be to do this, except it seems like there's some kind of Fibonacci thing going on here, because I believe that the roots of this polynomial are the golden ratio and some other sort of conjugate value with respect to the golden ratio, I think. Yeah, so these are the values of alpha and beta. And I know that the terms in the Fibonacci sequence can be written in terms of powers of alpha and beta. I don't remember exactly what the expression is. So maybe, and you know, the definition of bn, let me write down how an and bn are defined. Terms of the Fibonacci sequence can be written something like this. I don't know if this has to be, if the exponents are always the same. I guess they probably have to be with to cancel the root 5s. And but I don't know what's supposed to be in the denominator normally. I also don't remember exactly how to prove that, but I'm sure ultimately it's not terribly difficult. So which of the following options are correct? Okay, so I think the first thing I'm going to do is maybe try to figure out what exactly the relationship is between the Fibonacci sequence and the golden ratio. I think the general formula for a Fibonacci term, you might be able to prove it by induction, but typically that's the kind of thing, it's helpful to know what the result is before actually trying to prove it, right? Okay, so yeah, I think the AN terms are just the Fibonacci sequence. I think that's what I've ended up showing here in total. So I have both alpha and beta. I just started, alpha squared is equal to alpha plus 1. That comes from the definition of alpha, that it's the root of this polynomial. And then multiplying this by alpha, I have alpha cubed is equal to this, but I know that alpha squared is that, so I sub things back in appropriately. And then I computed alpha to the 4, alpha to the 5, always just taking whatever alpha squared is on the right-hand side, replacing with alpha plus 1 and simplifying. And you notice that the coefficients on the alpha term and on the constant term are always going to be terms in the Fibonacci sequence. So I have this relation here that alpha to the power of n is equal to the nth Fibonacci term times alpha plus the n minus 1 Fibonacci term. Same thing holds for beta. And then you can show that this term here simplifies just by subbing these things in here. This simplifies to the nth Fibonacci term. So what I have here then is AN is equal to the nth Fibonacci term. And then this sequence BN is defined as AN minus 1 plus AN plus 1. So this is just going to be AN minus 1 plus, and then I'm going to use the definition of the Fibonacci sequence to simplify this. We get AN plus AN minus 1. So I don't think options B or D are correct. These things about infinite sums. I don't see where they would come from. I think what I'm going to do is directly compute Bn in terms of alpha and beta to see if option C is correct. What if instead of trying to compute Bn in terms of alpha and beta, well, hold on. Yeah, okay, so Bn is equal to alpha to the n plus beta to the n. It's just a question of doing some algebra and substitutions and so on. This is how Bn is defined. I substitute the two definitions of an minus 1 and an plus 1, do some factoring. I use the relation, there's a relation between alpha and beta that I've used here in both spots. And then also 1 over alpha is equal to negative beta. So we get a cancellation of things everywhere. Okay, so that option is correct. And then is it true that the sum of Fibonacci terms, I think this is something that could be true. So this is looking like it's true, at least for the first 5 values of n. Yeah, so this I didn't do this terribly formally here, but I've essentially laid out some computations that could be turned into an induction argument. So we verified base cases. We verified the first 5 values of n that this works. And then what I've shown here is that, I take this, I split the Fibonacci term into those two, and then I further split this term into 2 others, so I get another copy of an and a copy of an minus 1. Okay, so, and then, if I assume that this is true for, n minus 1, like, why don't I just turn it into an induction argument? So we have this. We're going to assume that it's true for n minus 1, and then show it's true for n. So I add an to both sides. Was it really just that easy? Did I just have to do it that way? Yeah, I guess, that works there. There's, this is the induction step. Assume this is true, then just add an to both sides. That becomes an plus 2, and we're done. And we verified base cases, right? So option A is also correct. So we've got A and C are correct. My intuition is telling me that these last 2 are not correct, but this is interesting, right? Because we're basically saying take the terms in the Fibonacci sequence and write them as a decimal. Actually, maybe this could be correct, right? Because we've got there's the first several terms of Fibonacci. So this thing on the left is saying basically take the number whose decimal expansion in the decimal places, you insert these, and then of course when you had a 2-digit number, you carry over into the previous digit. So if I call this S, then S is equal to 0.112 3, 5, 8. Carry the 1, put a 3 there. I need more terms. 25. 38. And then what is it? 6, 63. 38 plus 63. 111, is that a Fibonacci number? Well, anyway, assuming it is. So we're continuing like this. 111 plus 60. I did something wrong. Yeah, these numbers are not correct. 21. I knew this didn't look familiar. 13 plus 21. 34. 21 plus 34. 55. 34 plus 55. 89. Okay. Oh, and it's interesting. We even get here, there's more carryover like that. So, I mean, if we do want to prove this, I don't think this is the right way of doing it. So I don't want to work on this one too much longer because the video is already pretty lengthy. I think I'll try just one or two more things trying to figure out whether this is true or not. But something else that I did notice is that the two options we're looking at here, the two whether these two sums are equal to a particular rational number or not. So this is the one I was working on just a minute ago. And we also have the sum of bn over 10 to the n is equal to 8 over 89. So these can't both be true. That's for sure, because an is less than or equal to bn for all values of n. In fact, bn is equal to an plus 2, an minus 1. So they can't both be true. And if either of them are true, I suspect it's this one, but just not really sure how to show that. Yeah, I'm not. So the viewer that submitted this said that it came from, the question comes from some kind of, I don't know if it's a test or a contest or something like that. I don't know if calculators are allowed to be used in this on this contest. Maybe this question could be answered pretty easily with a calculator. I'm not sure. I think for now, just because of how long this video is getting, I'm going to leave it here. So certainly options A and C are true. But in terms of options B and D, they can't both be true. but I really don't know for sure if one of them at all is true. So yeah, I'll leave it there. If I have more to say, or if I figure out definitively what the answer to this one is, I'll put it down in the description. Thanks for watching.